Sit with something before we explain a single thing. Imagine two scraps of the same material, one grown carefully in a spotless lab, pristine, almost perfect. The other a mess, grown sloppily somewhere else, on another continent, in another decade, shot through with impurities, the kind of dirty sample you'd normally throw away. Now measure one electrical number on each, and they come out the same, not close, not the same to within the usual wobble every real experiment has. Identical, carved to a sharpness that nothing about a messy, handmade material has any right to reach. As if all the mess, all the dirt, all the difference between the two simply did not count.
And that last word is the whole episode, so hold on to it. It did not count because what the machine is reading isn't really a property of the material at all. It's a count. It's a whole number. And a whole number is the one kind of answer nature is not allowed to fudge. You can have 3 apples or 4 apples. You cannot have 3 and a slightly dirty apples. So when a measurement locks onto a whole number and stays there, it stops behaving like a measurement and starts behaving like arithmetic. Arithmetic so exact, the world now uses it to define its own units.
Okay, that's a genuinely strange promise, and I already don't believe you, which feels like the right way to start. But you said electrical number, and my instinct is to reach for the most boring thing I know. Can we start from something I've actually measured on a lab bench?
Please, that's the whole spirit of this. Where do you want to plant your feet?
Ohm's law. Voltage equals current times resistance. That's the first real equation anybody hands you in electricity. You push current through something, a voltage builds up across it, and the ratio is the resistance. Resistance is just how hard the material fights the flow.
Perfect starting point, because resistance is exactly the kind of quantity that should be messy. It depends on what the stuff is made of, how dirty it is, how warm it is, how big the sample is. 2 different chunks of metal give you 2 different resistances, every material with its own fingerprint. Now let me add the one twist that turns this into a real story, and it's a twist you've also already done in lab. Have you done the Hall effect? Back to the Hall effect.
We did. You take a flat strip of conductor, run a current down its length, and then you turn on a magnetic field pointing straight through the face of the strip, at right angles to the current. And a voltage appears, but sideways, across the strip, not along it. The Hall voltage.
Right. So walk me through why that sideways voltage shows up. What's pushing on the charges?
It's the Lorentz force, isn't it? The charges are drifting along the strip, and a moving charge in a magnetic field gets pushed sideways. Force equals charge times velocity crossed with the field. So the carriers get shoved toward one edge, they pile up on that side and leave the other starved, and that separation of charge is a sideways voltage. Wait, this is just the Lorentz force pushing charges sideways, right? There's nothing more to it than that.
At this stage, nothing more to it than that. You've got it exactly. And here's the lovely, mundane punchline of the classical version. The charges pile up until the sideways electric field from the pile-up is strong enough to exactly cancel the magnetic push. A standoff. And when you work out that balance, the Hall voltage you measure comes out proportional to the magnetic field. Crank the field up, the sideways voltage climbs in a straight line. So if you plot the Hall resistance, that sideways voltage divided by the current, against the magnetic field, you get a straight, boring, rising line. A ramp.
And that ramp is actually useful if I remember right. The slope tells you how many charge carriers there are, and the sign tells you whether they're negative electrons or positive holes. That's the whole reason anyone runs the Hall effect in the first place. It's a way to count the carriers in your material.
It's the workhorse measurement. Carrier type, carrier density, mobility. The Hall effect hands you all of it, and it has since a graduate student named Edwin Hall discovered it in the late 1800s, before anyone even knew an electron existed. Genuinely old, textbook, settled, a straight line rising with the field. Get comfortable with that ramp, because the whole episode is about pushing this exact experiment somewhere brutal.
Define brutal.
2 knobs. First, make the sample two-dimensional. Trap the electrons in an incredibly thin, incredibly clean sheet, a single flat layer stuck at an interface inside a semiconductor device. Second, go extreme, a very strong magnetic field, far past anything you'd use in a teaching lab, and cool the whole thing to a whisker above absolute zero. Same measurement, same ramp you'd predict. Except it isn't a ramp anymore. The staircase.
What does it turn into?
A staircase. The smooth, rising line breaks into a series of flat steps connected by sharp risers. You crank the magnetic field up, and instead of the Hall resistance climbing steadily, it climbs for a bit, then flattens completely. Dead flat, a plateau, holds there while you keep cranking, then suddenly jumps to the next flat step, holds again, jumps again. A staircase where the textbook told you to expect a ramp.
That's already weird. Nothing in the Lorentz force story wants to make a step.
Nothing in that story does, and that's the tell that we've walked off the edge of the textbook. But here's the part that turned this from, weird steps into a revolution. Look at the height of each flat step. Those values aren't random, and they aren't set by your material. Every plateau sits at a fixed combination of 2 constants of nature divided by a whole number. Say it as a conductance instead of a resistance, and it's even cleaner. On each plateau, the Hall conductance is a whole number times E squared over h.
Slow down and make sure I know what those letters are. The E is the charge on a single electron, and the H...
The h is Planck's constant, the fundamental quantum of action, the number that shows up every time nature does something quantized. So E squared over h is a bundle built out of nothing but the electron's charge and Planck's constant. And now stare at what's not in it. There's no mass of the electron, no density of carriers, no size of the sample, no temperature, no measure of how dirty the thing is. None of the material appears at all. The step height is built purely from universal constants multiplied by a whole number.
Oh, that's what you meant at the very start. If the plateau height only contains E and H, and both are the same everywhere in the universe, then it literally cannot know whether my sample was clean or filthy. There's no slot in the answer for the mess to get into.
That's exactly it, and you got there faster than history did. The only thing that changes from plateau to plateau, the only thing your particular experiment actually contributes, is which whole number you're multiplying by. 1, 2, 3, which step you're standing on. So the experiment has stopped measuring a property of the material the way Ohm's law does. It's doing something much stranger. It's counting. It reads off an integer.
And this is the "a whole number can't be fudged" thing. Let me try to say why that matters. If a quantity is free to be anything, any value with a decimal, then every little imperfection nudges it a bit and the number drifts. That's why normal measurements wobble. But if a quantity is only allowed to be a whole number, a tiny nudge has nowhere to go. There's no tiny bit up the staircase. The next legal value is a whole step away. So between the jumps, it just sits there, exactly constant, forced to be.
You just explained the whole miracle better than most textbooks do. A quantity free to take any value wobbles with every speck of dirt. A quantity forced to be a whole number can only change by jumping, and between jumps it is exactly, boringly, gloriously constant. And that flat constancy is the perfection people measure in these labs. The Hall resistance on a plateau agrees from sample to sample, lab to better than a part in a billion. The messiness doesn't count because the answer is a count.
But you've smuggled in the hard part. Why is the number forced to be a whole number in the first place? Ohm's law doesn't force anything to be an integer. What is it about this cold, two-dimensional, strongly magnetized situation that says, your answer must be a whole number, no fractions in between?
That is the exact right question, and answering it is the reason 3 people won a Nobel Prize decades after the effect was found. The answer has a name, and the name is topology. Let me build it, slowly, because the word gets thrown around like a magic spell, and I refuse to do that to you. Why a number can't drift. Ask yourself, where else in life do you meet a number that's forced to be a whole number, that can't drift, that can only change by a sudden jump? Not a measured number, a counted one. The number of holes in a surface, for instance.
Holes in a surface. Like, a doughnut has 1 hole, a ball has none.
Exactly that. And this is the picture the Nobel Committee itself reached for. One of them actually stood up at the announcement with a tray of pastries. Here's the game. Take a doughnut made of soft clay. You're allowed any smooth, gentle reshaping you like. Squash it, stretch it, dent it. You are not allowed to tear it or punch a new hole. Now, can you turn that doughnut into a coffee mug?
Into a mug? The handle is the hole? Yeah, actually. You push a dimple in the top for the cup and let the ring become the handle. 1 hole the whole way through. So, to a topologist, a doughnut and a coffee mug are the same thing.
The same thing. 1 hole each. And a pretzel is a different thing because it has more holes, and no amount of gentle squashing gets you from 1 hole to several. Here's the point that matters. Through all that squashing and denting, the number of holes never changed. It couldn't. It's a whole number, and there's no 1.5 holes that you could smoothly pass through on the way. The only way to change the count is to do something violent, to tear. That kind of quantity, a whole number that survives all smooth deformation and only jumps when you rip the thing, is what mathematicians call a topological invariant.
Okay, but now I need you to be really careful with me because I can feel the analogy wanting to run away. There is not literally a doughnut inside my silicon chip. The electrons are not sitting in a ring with a hole in the middle. So what is actually the surface here, and what is actually the hole?
Thank you for stopping me there, because if you let that picture harden, it becomes a lie, and this whole conversation lives or dies on not doing that. You're right. There is no literal doughnut, and no literal hole in the sheet of electrons. The surface I'm counting holes on is not made of matter at all. It's an abstract space, the space of the electron's quantum states. Remember from your first quantum course that the electrons are described by a wave function. As you sweep through all the momenta the electrons can have, that collective quantum state twists and turns, and the number I keep calling the whole number is a kind of winding, how many times the quantum state wraps around as you make that sweep. That winding is a topological invariant in exactly the doughnut sense, a whole number that can't drift. The pastry is a picture of the mathematics. It is not a claim that the material has a hole in it. Keep the picture, throw away the dough.
Got it. The hole is in the math of the quantum state, not in the metal. So the Hall conductance is stuck on a whole number because that number is one of these windings. A topological count of how the electron's quantum state wraps around. And dirt in the sample.
Dirt in the sample is a smooth deformation. That's the key move. An impurity, a bump, a warm spot, a ragged boundary. From the state's point of view, all of that is squashing and denting the clay. It dents the state. It does not tear it, and a dent can't change a whole number winding. So the count holds, and because the count holds, the conductance holds, to a part in a billion, no matter how ugly your particular sample is. That's the answer to the question we opened with. The mess doesn't count because the answer is a topological count, and a topological count is deaf to smooth mess.
There's a second analogy I've heard for this. a knot in a rope or a coiled-up cord you can't untangle. Is that the same idea or a different one?
Same idea, useful for a slightly different reason, so let me use it. Carefully. Wind a cord around a post a few times. The number of times it winds is a whole number, and you can shake it as hard as you like, the winding won't change. To change how many times it's wrapped, you have to cut the cord. And here's why I love this one. It makes obvious that the protection is real, but not infinite, because there is a way to change the number. You cut. In the real material, cutting means something specific and physical. These topological states are protected by an energy gap. Think of it as a moat that keeps the winding safe. If you push hard enough to close that moat, heat the sample up too much, crank the disorder past a breaking point, or drive the system through a genuine change of phase, you've cut the cord and the number is free to jump. So, protected means robust against small, gentle, local mess. It does not mean indestructible. Tear the thing and topology gives you nothing.
That's a distinction I want to hold on to, because immune to dirt was starting to sound like immune to everything, and those are really different claims.
Wildly different, and the gap between them is where a lot of hype lives. Protected against local disorder, true, provable, measured. Immune to everything, false. The moat can be crossed if you throw enough at it. Now let me show you the most beautiful consequence of this whole idea. It takes the winding out of the abstract and puts it somewhere you can almost see. The one-way highway. Think about the boundary of the sample, the physical edge of the sheet. It turns out that when the inside of one of these materials is locked into a topological state, something has to give at the edge, where that state meets ordinary empty space outside. And what gives is this. The material can be a perfect insulator on the inside. No current flows through the bulk at all, while the edge becomes a conductor. Current runs only around the rim.
That already sounds backwards. Normally, if something conducts, it conducts through the middle. You're telling me the middle is dead and the border is alive?
The border is alive, and the middle is dead. And that combination even has a name, a topological insulator. Insulating in its interior, conducting on its boundary. And those edge channels are protected in the same topological sense, with a wonderfully concrete way to picture why. On these special edges, the electrons can only move in one direction. The channel going one way around the rim is physically separate from the channel going the other way. Two one-way streets on opposite sides of the sample. So picture an electron running along the edge, and it hits an impurity that would normally bounce it back. To bounce back, it would have to reverse direction. But there's no lane going backward on its side. There is simply nowhere for it to scatter to, so it can't turn around. It just keeps going, right past the dirt, as if the dirt weren't there.
Oh, that's gorgeous. It's not that the electron is shielded from the impurity, it's that turning around isn't one of the options the universe is offering it. A one-way highway with no oncoming lane.
A one-way highway with no oncoming lane. That's exactly the phrase and the cleanest picture in the whole subject. And it's the same deep reason as before, in new clothes. Stopping that edge current would mean changing the topological number of the inside back to the ordinary one. And it can't do that smoothly, because that's a tear, not a dent. So the edge keeps conducting through dirt that would kill an ordinary wire. And let me label the limit, because I promised I always would. This is the clean, idealized story. Real edges are at a real temperature, have a finite length, and always carry a little residual scattering. The edge conduction is close to perfect and astonishingly robust. But protected here means robust, not eternally indestructible. The protection is real, and it is not magic.
I appreciate that you keep drawing that line. So this isn't just one weird measurement, it's a whole family of materials where the topology of the inside forces something protected onto the outside.
A whole family. and it's been one of the biggest themes in physics of the last 20 years. And here's where I get to hand you the real history, because everything I've described actually happened in a specific order to specific people, and the true story is better than the analogy. From a lab curiosity to the kilogram. The staircase came first, and it came by surprise. In the spring of 1980, a physicist named Klaus von Klitzing was working at a high magnetic field laboratory in Grenoble, in the French Alps, studying one of those clean two-dimensional electron sheets inside a silicon device. And he saw the plateaus, the flat steps, sitting at whole number values with an accuracy that stopped him cold. In his original data, the plateau heights matched the whole number rule to better than 1 part in 10 million. Not 1 part in 100, not 1,000, 10 million. When a messy solid-state device does something that clean, you know you found a law, not an accident.
And that's the one that gets called the integer quantum Hall effect. Integer because the steps are at whole numbers.
The integer quantum Hall effect, exactly. And von Klitzing won the Nobel Prize in Physics for it in 1985. And I want to be precise about this because these prizes get blurred together and they shouldn't be. That 1985 prize was his alone, awarded solely to Klaus von Klitzing for the discovery of the quantized Hall effect. Hold that, because 2 more prizes are coming and the casts are all different.
Noted. Solo, 1985. So what happened next? You keep promising me this ends up defining the kilogram, which still sounds insane.
It does end up there, and here's the road. Because that plateau value is built only from E and H and a whole number, because it genuinely does not care about your material, it is the most reproducible electrical quantity anyone had ever found. Any lab, any sample, any continent, the same number. So metrologists, the people whose job is defining units, pounced on it. The resistance of that first plateau became the world's resistance standard. It even has a name, the von Klitzing constant. Planck's constant divided by the electron charge squared, h over E squared, which comes out to about 25,813 ohms. From then on, 1 ohm could be pinned to a whole number and 2 constants of nature, instead of to some fraying artifact in a drawer.
And then it goes further than resistance, doesn't it? You said the kilogram.
It goes all the way. In the year 2019, the world's official system of units was rebuilt from the ground up. Instead of defining units by physical objects, like that infamous lump of metal in a vault near Paris that used to be the kilogram, they did something far more elegant. They fixed the numerical values of a handful of constants of nature exactly by international agreement, once and for all. Planck's constant h fixed, the electron charge E fixed, and once those numbers are nailed down as exact, the kilogram can be defined through h and the unit of electric current, the ampere, through E. Mass and current now defined in terms of quantum constants.
But wait, that's a definition on paper, fixing some constants. Where does the actual quantum Hall staircase come in? A definition isn't a measurement.
That is exactly the right thing to pin down. The definition is just the fixing of the constants. What the quantum Hall effect provides is the bridge, the practical way a real laboratory turns that paper definition into a calibrated instrument. When a national lab realizes these units, it uses the quantum Hall effect for resistance, together with a partner quantum effect, the Josephson effect, for voltage, in an instrument called a Kibble balance that plays an electromagnetic force off against a real weight. So the honest way to say it is, the quantum Hall effect does not define the kilogram, the fixed constants do, but it's how we cash that definition out into reality. A staircase in a cold, dirty semiconductor is the practical foundation under the modern kilogram and ampere. That still amazes me.
That's a much better sentence than quantum physics defines the kilogram, and it's the true one. And your careful phrasing makes me suspect the story doesn't stop at whole numbers.
You're learning to hear the setups. It does not stop at whole numbers. Push the same experiment even harder, stronger field, colder and cleaner sample, and in 1982, two physicists at Bell Labs, Daniel Tsui and Horst Stormer, found new plateaus in between, and these were at fractions. The most famous sits at 1/3.
1/3 of a step? But you just spent all this time convincing me the whole point is that it has to be a whole number. How do you get 1/3 of a whole number that can't be divided?
And that was exactly the reaction of the whole physics community. It looked like a contradiction. The resolution, worked out by Robert Laughlin within about a year, is one of the deepest ideas in the subject. At those extreme conditions, the electrons stop behaving like a crowd of separate particles and condense together into a completely new kind of quantum liquid, a single, collective, incompressible quantum state. And when you poke that liquid, the little disturbances that ripple out, the quasi-particles, behave as if they carry only a fraction of an electron's charge. At the 1/3 plateau, they act as though they carry 1/3 of the charge of an electron.
1/3 of an electron's charge. But an electron is supposed to be indivisible. You can't split one. My intro course was very firm about that.
And your intro course is right. You cannot chop an electron into pieces. No single electron has been split. This is subtler and cooler. The fractional charge is a property of the collective disturbance in the liquid, an emergent thing the whole crowd of electrons conspires to produce that behaves like a fraction of a charge, even though every electron is still perfectly whole. A genuine new form of matter, and it earned its own Nobel Prize. 1998, a trio, Laughlin, Stormer and Tsui, together for discovering a new quantum fluid with fractionally charged excitations. Different prize, different year, different people from von Klitzing. Keep the casts separate.
Solo in 85, trio in 98. And I have a feeling those fractional charge quasi-particles are special beyond just the fraction.
They are, and this is the piece that points straight at the frontier. You know there are two kinds of particles, fermions, like electrons, and bosons, like photons. The deep difference is what happens when you swap two identical ones. Do the swap, and the quantum state either stays exactly the same, bosons, or picks up a flat minus sign, fermions. Those are the only two options. Except only two options turns out to be a fact about three-dimensional space. Confine the world to a flat, two-dimensional sheet, exactly what these Hall systems are, and a third possibility opens up. Excitations where swapping two of them multiplies the state by something in between. Not a plus, not a minus, but a fractional twist. Particles like that are called anyons, because the twist can be, loosely, anything.
Anyons, and any because they're not stuck with the boson plus sign or the fermion minus sign. They can land in between. But is that a real thing anyone has seen? Or is it a theorist's daydream?
This is where I get to be precise about proved versus hoped, the most important habit in this whole subject. For a long time, anyons were exactly a theorist's daydream, beautiful, predicted, unconfirmed. But in the year 2020, that changed. Two independent experiments, one an interferometer that sends these quasi-particles around a loop, one a collider that smashes streams of them together, directly detected the fractional twist. Braid two of these 1/3 quasi-particles around each other, and the quantum state really does pick up that in-between phase, the way anyon theory said it would. So as of 2020, anyons are real. That one I can state flatly.
That's a big deal. But you look like you're about to add a fence.
I am, and it matters for where we're going. The anyons confirmed in 2020 are what we call ubili un anyons. Braid them and the state picks up a twist, a phase, and that's it. That's real, confirmed, at the 1/3 state. But there's a second, wilder class predicted to exist: non-ubili anions. For those, braiding doesn't just multiply the state by a phase, it rotates the state among several genuinely different possibilities, and, crucially, the end result depends on the order in which you did the braids. Those are the ones that could, in principle, be used to compute, and those have not been confirmed. They are sought, not found. Keep that line bright. Ubili anions, seen, 2020. Non-ubili anions, still hoped for.
Ubili unseen, non-ubili unhoped. And where did the word topology finally get its own prize? You've mentioned it as the reason for everything, but the prizes so far were for the effects, not for the idea.
Right, and that's the third prize, and it closes the loop beautifully. In 2016, the Nobel Prize in Physics went to 3 theorists. David Thouless got one half, and Duncan Haldane and Michael Kosterlitz shared the other, for theoretical discoveries of topological phase transitions and topological phases of matter. That's the prize that officially crowned topology as the hidden organizing idea behind all of it. Thouless was the one who, back in 1982, showed with his collaborators that von Klitzing's mysterious whole number really is a topological winding, the doughnut count made rigorous. That's the moment the field understood why the staircase is so perfect. And it's the prize where a committee member stood up in Stockholm and explained the whole thing to the world's press using a cinnamon bun, a bagel, and a pretzel.
Physics explained with a pastry tray. I love that that's the official record. So let me take stock. We've come a long way from Ohm's law, and it's all remarkably solid ground. An exact staircase, a topological winding behind it, a count that underpins the world's units, a fractional cousin whose anions we've now watched braid, and a Nobel for topology itself. So what's the part nobody's figured out yet? Where's the edge?
Now we're at the horizon, and it's a good one. A genuinely world-changing idea sitting right there, gorgeous and unproven, with some of the biggest companies on Earth betting on it, while a lot of physicists shake their heads. Let's go carefully. The horizon, a qubit made of shape. Here's the dream. The great obstacle to building a quantum computer is fragility. A quantum bit, a qubit, holds its information in a delicate superposition, and the faintest disturbance from outside, a stray bit of heat, a stray magnetic wobble, corrupts it. That's the whole nightmare of the field. Qubits forget almost instantly, and you pour enormous effort into correcting their errors faster than the world can scramble them. Now think back over everything we said tonight. What if you could store the information not in something fragile and local, but in a topological winding, a whole number that, by its very nature, a local disturbance cannot change? A dent can't corrupt a count. That's the idea of a topological qubit. Bake the error protection into the topology itself so that noise, which is always local and gentle, simply can't reach the information.
Oh, that's a beautiful idea. Instead of frantically correcting errors, you build the qubit so that the errors are topologically forbidden in the first place, the same way the dirt couldn't turn the edge electron around. You'd store the bit in something that can only be changed by a tear, and then just don't tear it.
You've understood it completely, and that's precisely why it's such a seductive dream. The same protection we spent the whole episode admiring, aimed at the single hardest problem in computing. The concrete plan is to build it out of non-abelian anions, the wild ones whose braids remember their order. You'd store quantum information in how those anions are braided around each other, and because braiding is topological, the information would inherit that protection. The most pursued version uses a specific excitation called a Majorana mode. The idea being that a specially engineered wire, made of the right combination of materials, is supposed to host one of these at each of its ends.
Supposed to host. You said that very deliberately.
I did, and here is where I have to be the honest guide rather than the salesman, because this is the part of the story where the hype is thickest and you deserve the truth. Topological quantum computing has not been achieved. There is no working topological qubit. It is, right now, a hope. A spectacularly promising one, but a hope. And the building block it depends on, the Majorana zero mode, is itself contested. Its existence in these wires is not settled science. Let me give you the actual recent history, because it's a case study in how science polices itself.
Please. I'd rather have the messy real story than a press release.
Then here it is, straight. In 2018, a prominent research group published a paper in the journal Nature reporting a clean signature of a Majorana zero mode, celebrated as a milestone. A few years later, in 2021, that paper was retracted. The authors themselves concluded they could no longer claim to have observed it. The evidence didn't hold up to closer scrutiny. That's the system working, by the way. Painful, public, but working. Now jump to early 2025. Microsoft announced a chip it called Majorana 1, presenting it as the first quantum processor with a topological core, carrying a small number of qubits, 8, and a stated roadmap toward 1 million someday.
8 qubits now, 1 million on the roadmap. That's a huge claim. Did it hold up?
That is exactly the live dispute, and I have to report it faithfully rather than tell you how it ends, because it has not ended. The scientific paper that accompanied the announcement demonstrated a device and a particular measurement on the wire. But crucially, the editors of the journal that published it added an explicit note. The results do not represent evidence for the presence of Majorana zero modes in the reported devices. The journal itself flagged that this is not a demonstration of the very thing the technology is named after. On top of that, an independent physicist published a peer-reviewed challenge to the topological qubit claims, and coverage across the science press reported that most physicists in the field remain unconvinced. The company has shown further results at conferences since, but those have not yet been through peer review. So the honest status today is an active, unresolved dispute, not a breakthrough you can bank on.
Let me make sure I'm holding this correctly, because it would be so easy to walk away with the wrong sentence. Nobody has built a topological qubit. It is not even settled that the Majorana modes it would be built from exist in these wires at all. There's a real claim from a serious company. There's serious peer-reviewed pushback, and the journal itself put up a flag. So the right thing to feel is neither it's done nor it's fake. It's this is genuinely unresolved and we're watching it get fought out in real time.
That is exactly the sentence, and holding it is what separates understanding the frontier from being sold the frontier. Notice the shape of it. The integer quantum Hall staircase, rock solid, it defines your units. The fractional effect and its fractionally charged quasi-particles, real. Abeli und anyons braiding, directly seen in 2020. Topological insulators with their protected, dirt-defying conducting edges, realized in the lab back in 2007. All of that is proved, I'll say it flatly, and sleep fine. But a topological qubit built from non-Abeli und Majorana modes, protected by topology from error, that is hoped. Beautiful, motivated, unbuilt, contested. And the honest version is more thrilling than the hype, not less, because it means the question is still wide open, and open questions are where you come in.
Say more about that, because I think it's the real ending.
Think about what would be true if it worked. Everything we admired tonight, the staircase that ignores dirt, the edge that can't be turned around, the count that only a tear can change. All of that protection, redirected to shield the most fragile and valuable thing in modern technology: quantum information. A computer whose reliability isn't patched on afterward, but woven into the shape of the material itself. That's the prize, and nobody has claimed it. Maybe nature won't allow a Majorana mode to sit cleanly at the end of a wire. Maybe it does, and someone finally nails the measurement. Maybe a different non-li-un anyone somewhere else is the one that works. All three are live, and the people who will settle it are, more or less, your age right now.
Let me try to say the whole arc back to you honestly. We started at Ohm's law and the Hall effect, the Lorentz force pushing charges sideways, a straight rising line, pure textbook. We turned two knobs, the field and the temperature, and the line shattered into a staircase whose steps are exact to a part in a billion, because each step is a whole number. A topological winding, a count that dirt can dent but can't tear. That same idea gives us edges that conduct through disorder because turning around isn't an option, and materials that insulate inside and conduct only on their skin. That count is now the practical foundation under the kilogram and the ampere. There's a fractional cousin whose fractionally charged anyons we've directly watched braid. Topology got its Nobel in 2016, and out past all that solid ground is the dream of a qubit protected by shape itself. Not built, it's Majorana building block still contested, being argued over in public right now.
That is a flawless summary, and the fact that you can hold the proved part and the hoped part in two separate hands without letting either blur into the other, that is the entire skill. That's what being a physicist actually is. So here's what I want you to walk out with. Not long ago, every piece of this was unthinkable. A resistance so perfect it embarrasses our best rulers, a charge that comes in thirds, a particle that remembers being swapped, a computer that might one day be protected by the same stubbornness that makes a doughnut refuse to become a sphere. And the whole edifice starts exactly where you started tonight. A current, a magnetic field, and the Lorentz force pushing charges sideways. That's the homework you've already done. The frontier is one cold, strong field step past it.
One step past the homework. Again. I keep expecting the frontier to be a different country, and it keeps turning out to be the next room.
It's always the next room. Go look at the staircase. The real plots are out there. Flat plateaus stacked like steps, exact to a part in a billion, measured in dirty little chips all over the world that agree to a precision they have no earthly right to reach. And then go do your next problem set, knowing that the difference between a textbook exercise and a Nobel Prize is sometimes just how hard you're willing to turn the knobs.
I love that. Until next time, keep an eye on the edges. That's where everything interesting is protected and where the frontier is still being argued.